Welcome to another lesson of Math 1314 College Algebra. Today we'll be discussing Section 2.7 Linear Inequalities and Absolute Value Inequalities. In this section we will use interval notation, we'll use properties of inequalities, we'll solve inequalities in one variable algebraically, and we will solve absolute value inequalities. The very first thing that we'll discuss is using interval notation. So we need to discuss first the definition of what interval notation is. To define or notate solution sets. Another way is using set builder notation that has curly braces. Where we have something like the set of all x such that x is greater than or equal to 2. That's another way to do this. What is another way that we can represent an inequality? Well, we could also represent that as just x greater than or equal to 2. So we have 3 different ways so far that we can list this. Now, let's move on and discuss various ways of looking at different sets and how they're indicated, as well as what those look like in set builder and interval notation. Let's build a table. Now let's discuss all the possibilities for sets indicated and what they look like in set builder notation and interval notation. So first, let's look at all real numbers between a and b, but not including a or b. That is, and we'll change colors here, it is the set of all x's such that a is less than x, which is less than b. How would we write that in interval notation? Well, we're not including a or b, so it's the interval from a to b, and we use parentheses to indicate that those values are not included. Let's move on to the second one. All real numbers greater than a, but not including a. Well, this is the set of all x such that x is strictly greater than a. Well, our lower limit is a, and the upper bound is infinity. So we have from a to infinity. Let's move on to the third one. All real numbers less than b, but not including b. Okay, that gives us the set of all x's such that x is less than b. In interval notation, that's negative infinity up to b, but not including, so we use a parenthesis. The next one is all real numbers greater than a, including a. Well, this is the set of all x such that x is greater than or equal to a instead of just greater than. And the interval notation is not a parenthesis, but a bracket to include a to infinity. Infinity always has a parenthesis because it's not a specifically defined number. Okay, all real numbers less than b, including b. Well, in set builder, that's the set of all x's such that x is less than or equal to b. And interval notation, that's negative infinity to b with a right bracket to show that b is included. Okay, all real numbers between a and b, including a. Well, that's the set of all x's such that a is less than or equal to x, which is strictly less than b. In interval notation, that is a left bracket on a and a parenthesis on the right side for b, because b is not included. The next example is all real numbers between a and b including b. That's the set of all x such that a is less than x less than or equal to b, and then an interval notation that is a parenthesis on a and a bracket on b, and then all real numbers a and b including a and b. That's the set of all x such that a is less than or equal to x less than or equal to b, or in brackets a comma b. All real numbers less than a or greater than b. Well, that's the set of all x such that x is less than a or x is greater than b. In this case, we have to have two separate intervals, which is a union of intervals, which means both are included. It's an or. We have negative infinity up to a, not including a, union from b to infinity, not including b. And then finally, all real numbers. Well, that's the set of all x such that x is a real number. Close that curly brace. And the interval is negative infinity to positive infinity. So that gives us basically all the cases for specific sets on real numbers, set builder notation, and interval notation. So now we can move on and do some examples, and then we'll move on to the properties of inequalities. Let's do an example involving interval notation. Use interval notation to indicate all real numbers between and including -3 and 5. So we're in the case where we have two real numbers and our x, the number we don't know, that helps build the whole set that we're considering, has to be between -3 and 5, and we know that we include both -3 and 5. So we use brackets instead of parentheses to show that we include both of those. Could we write this in set builder notation or as just an inequality? Well, as just an inequality, -3 is less than or equal to x is less than or equal to 5. And set builder is the set of all x such that x, we need to rewrite this just as our inequality, -3 less than or equal to x less than or equal to 5. Now what we were asked for was interval notation, but I wanted to go ahead and show you that we can do the others as well. Let's try another example. Express all real numbers less than -2 or greater than or equal to 3 in interval notation. Now I want to draw your attention to the fact that we have an or inside of this statement. We need all of the real numbers less than, so x less than -2, or x greater than or equal to 3. Well, what that tells us is that we need two separate intervals. So the first interval is all of the things from -infinity up to -2, not including -2. And then we need a union, that's what the or means. all of the numbers, including 3, up to infinity. And that's our final answer. Let's move on and consider some properties of inequalities. Let's consider some properties of inequalities. Let's first consider the addition property. If we know that A is less than B, then we also know that A plus C is less than B plus C. Okay? Let's talk about the multiplication property. Now, notice that the addition property is exactly the same as when we're dealing with equations. The multiplication property is a little bit different. So if A is less than B and C is greater than 0, then A times C is less than B times C. You notice we have to have that and there. If A is less than B and C is less than 0, then A times C is actually greater than B times C. Because that means that A times C is multiplying by a negative number, just like B times C is. So that flips our inequality symbol. These properties also apply to A less than or equal to B, A greater than B, and A greater than or equal to B. So it holds in every case for inequalities. It's always true that if we have A less than B, A plus C is equal to B plus C. That's always true for the addition property. And then we have conditions on what we're multiplying by that determines whether the sign stays the same or whether it changes because of a negative. Let's consider some examples. Let's try the following example. In this case, we want to solve the inequality 3x minus 2 less than 1. So we'll proceed just like we would with an equation, except we have an inequality this time, and we'll use the addition property of inequality to add 2 to both sides, and we get 3x is less than 1 plus 2, which is 3. Then we can use the multiplication property to divide both sides by 3, the coefficient in front of our variable. The 3's on the left-hand side will cancel, and I have x is less than 3 over 3, so x is less than 1. And that is our solution. We want to solve 4x plus 7 is greater than or equal to 2x minus 3. What's the first step that we do? Well, we can subtract 7 from both sides, and that leaves us with 4x greater than or equal to 2x minus 10. Then we can subtract 2x from both sides, and we get 2x is greater than or equal to negative 10. Then we divide both sides by 2. The 2's cancel. X is greater than or equal to negative 10 over 2, or x is greater than or equal to negative 5. And that's our final answer. Let's try another example. In this example, we want to solve the inequality and write the answer in interval notation. we have negative x plus 4 less than 1/2 x minus 1. The first thing we'll do is we'll subtract 4 from both sides. We have negative x less than 1/2 x minus 3. 1 minus 4 is 3. And then we subtract 1/2 x from both sides. And we have a negative x minus 1/2 x gives us negative 3/2 x less than negative 3. Then we can multiply both sides by 2, and we get negative 3x is less than negative 6. Then we divide by negative 3 on both sides. Now, again, we're dividing by a negative number. The negative 3's cancel. We have x. The sign has to flip and be greater than negative 6 divided by negative 3 is 2. Again, notice that when you divide or multiply by a negative number, you have to change the direction of the inequality. So we have that x is greater than 2. Are we finished? Well, no, we were asked to write this in interval notation. So this is the set of all numbers that are all numbers x that are greater than 2, not including 2. So our interval is from 2 to infinity, and that's our interval notation. So that is our answer. In this case, we have negative 5/6 x less than or equal to 3/4 plus 8/3 x. We want to solve this inequality and write the answer in interval notation also. So what can we do here? We have fractions on both sides of the inequality. So I think the first thing that I would like to do is to multiply by the least common denominator and clear those denominators out. So our factors are 6, 4, and 3. Those are our denominators. What's the first thing that we can use? We can multiply both sides by 12. So 12 divided by 6 is 2 times a negative 5x less than or equal to 12 divided by 4 is 3, so we have 3 times 3. 12 divided by 3 is 4 times 8x. Okay, so we have negative 10x is less than or equal to 3 times 3 is 9, plus 8 times 4 is 32x. Okay, we can subtract 32x from both sides. So we're left with negative 42x is less than or equal to 9. We divide both sides by negative 42. So we have to change the sign. So x is greater than or equal to negative 9 over 42. Can we simplify that any? Well, both are divisible by 3, so x is greater than or equal to negative 3 over, what's 42 divided by 3? 14. So x is greater than or equal to negative 3 over 14. In interval notation, that is in a bracket this time, because we're including 3/14, negative 3/14, that is, up to infinity. So all things greater than or equal to negative 3/14. So this is your answer. What happens if we have multiple inequalities in one statement? Well, a compound inequality includes two inequalities in one statement. For example, if we have 4 less than x less than or equal to 6, that includes 4 less than x and x less than or equal to 6. So that compound inequality takes this and that. So the 4 less than x and the x less than or equal to 6. Okay, so we can also solve compound inequalities. We can do that by either handling each of the inequalities separately or by doing operations to each term, each part of the inequality. And as long as we perform operations on all three at the same time, then we continue to have true statements as we go forward. So let's do an example. We want to solve the compound inequality. The compound inequality 4 less than 2x minus 8 less than or equal to 10. So how would we start? Well, we want to isolate x by itself. So let's add 8 to all three parts of the inequality. So we get 12 is less than 2x is less than or equal to 18. We can divide all three by 2 to get 12 divided by 2, which is 6, less than, the 2's cancel, x, less than or equal to 18 over 2, which is 9. So what this means is that we have all the values for x that are bigger than 6, x greater than 6, and all the things x less than or equal to 9. How would we write this in interval notation? Well, it doesn't include 6 and does include 9, so we include a bracket there. So these are all the numbers between 6 and 9, not inclusive of 6 and inclusive of 9. Now let's consider absolute value inequalities. If we have an algebraic expression x and k is greater than 0, then the absolute value of x, our algebraic expression less than k, is the same as saying that x is between negative k and k. So when we see the absolute value, we can rewrite absolute value of x less than k as negative k less than x less than k. The same is true when we have a greater than, except we have to break it into parts. If the absolute value of x is greater than k, then x is less than negative k, or x is greater than k. These statements are also true when you have the absolute value of x less than or equal to or greater than or equal to k. So let's do an example. Describe all x values within a distance of 3 from the number 2. Okay, so how do we do this? Well, we want the distance between our x value and the number 2 to be less than or equal to 3. So how can we rewrite that? Well, we can write the distance from x to 2 as the absolute value of x minus 2. That gives us the distance from 2, and we want that to be less than or equal to 3. So in this case, what does that give us? Well, we get two separate inequalities, or a compound inequality. It says that x minus 2 is between -3 and 3. So we can add 2 to both sides, or all 3 parts, not both sides, because we don't have just 2. So we have -1 is less than or equal to x, less than or equal to 5. Okay, so how do we write this in interval notation? It's all of the x's, including -1, from -1 to 5, including 5. Rewrite that right bracket because it doesn't look very good, but that is our answer. These are all of the x values within a distance of 3 from the number 2. Let's do a word problem as our last example. The high temperatures over the last 3 days were 63, 68, and 72 degrees. What must the high temperature be on the 4th day to have an average temperature of at least 72? Well, how do we find this out? What do we know? We know that we want our temperature to be at least 72. So we want our average temperature to be greater than or equal to that amount. How do we find the average? Well, we add up all of our values, which are 63, 68, 72, and then the value we don't know, which is the 4th day's high temperature, and we divide by the total number of days, which is 4. So can we solve this and figure out what temperature has to be on the 4th day to give at least a 70? Well, we can add those values together. 63 plus 68 plus 72 is 203. 203 plus x over 4 is greater than or equal to 72. We can multiply both sides by 4 to get 288, and then that leaves us 203 plus x. So 203 plus x is greater than or equal to 288, and then we subtract 203 from both sides, and we get x is greater than or equal to 85. So the only way that our average temperature over those 4 days can be 72 is for us to have a temperature on the 4th day of at least 85 degrees. So the temperature must be 85 degrees or higher for the 4-day average to be greater than or equal to or equal to 72. That concludes section 2.7 on linear inequalities and absolute value inequalities. Please let me know if you have any questions. Send those by email, and I will get back to you.